Hello, this is the second example class for the revision week and for linear algebra. And in this example class, we'll consider exam from 2016. And we're going to solve all problems on linear algebra from this exam. Yeah. Let's start with first problem. First problem is A4. It consists of three parts, A, B, and C. And this problem is about definition of linear subspaces. Which of the following subsets in R3 are linear subspaces? One is subset U, which is basically given by consists of vectors x, y, z in R3, such that x is non-negative, y is non-negative, and z is non-negative. Yeah. This is not a vector subspace. Why? We just need to provide an example. Vector 1, 1, 1 is contained in this vector subspace, but if you multiply it by -1, it's not contained in this subset. So this is not a linear subspace. Okay, so here the answer is no. In the second case, answer is also no. In the second part, in this case, the subset V is given in R3 by the equation x, y, z equals 0. Again, we need to provide a counterexample. So, for example, we can take a vectors 1, 1, 0. It's contained in V. Yeah. And we can take vector 0, 0, 1. It's also contained in V. But if you take the sum, you get vector 1, 1, 1. It is not contained in V. This is a contradiction. If V would be a linear subspace, then sum of any two vectors in V should be in V, which is not the case. And finally, final part is a bit trickier. So W, which is empty set. Yeah. This is also not a linear subspace. Why? Because zero vector is not contained in W. Remember, by definition, every linear subspace must contain zero vector. In this case, empty set doesn't contain zero vector, so it's not a linear subspace. Okay, good. So let's go to the next problem, which is problem A5. Okay, I must admit A5 is a boring problem. We get a matrix -1, 2, 2, 0, 2, -4, -3, 1, 1, 0, 1, 3, 2, and 5, 1, 2, 0. Okay, the question is find the reduced row echelon form of the matrix and compute its rank. So A is this, find reduced row echelon form of A and compute its rank. Okay, so there are two ways how we can proceed. The first way, basically, we just perform elementary row operations to get a reduced row echelon form. Okay, we start with R2. We subtract, we add first row to the second, multiply by 2, and we multiply first row by 5 and add to the fifth row. So let me shortcut it like this. Yeah. Fifth row goes to fifth plus 5 R2. and we get the matrix minus 1, 2, 2, 0, 0, 0, 1, 1, 0, 1, 3, 2, 0, 11, 12, 0. Yeah. What we can do, we, for example, can multiply first row by minus 1, and let's subtract third row multiply by 11 from the fourth row. Minus 11 times R3. Okay, I don't have space here, so let me put it here. So I get 1 minus 2 minus 2, 0, 0, 0, 1, 1, 0, 1, 3, 2, and then I get 0, 0, and here I get minus 21, minus 22. Okay, and now what we can do, we can subtract second row from the fourth, multiply by 21. So R4 goes to R4 plus 21 R2. Yeah. And also we can, I don't know, it's not necessary, but still I think it's okay. We can subtract after this from third row, second multiply by 1. Yeah. By 2. Or maybe by 3. We want to make this to be 0, this to be 0. Yeah, okay. Let me see. Yeah. Okay. So we get a matrix. This is still the same. This is the same. This is gonna be this, and the final row gonna be 0 and minus 1. Yeah. Okay, I don't have space here, so let me go to the next slide. So let me repeat, I had a matrix 1, minus 2, minus 2, 0, 0, 1. Okay, let me, wait. Yeah, 0, no, 0, 1, 1, 0, 1, 0, minus 1, and 0, 0, 0, minus 1. Yeah. Now, okay, what can I do now? I can swap these two rows. R3 swap with R2, yeah, and I get matrix 1, minus 2, minus 2, 0, 0, 1, 0, minus 1, 0, 0, 1, 1, 0, 0, 0, minus 1. Okay, let me also multiply this by minus 1. So I can erase this sign. Yeah. Okay, and now I can subtract fourth row from the third one. Minus fourth. Yeah. And I get matrix 1, minus 2, minus 2, 0, 0, 1, 0, minus 1, and 0, 0, 1, 0, 0, 0, 0, 1. And let me also the same time subtract, add fourth row to the second one. This would erase me this entry. So don't do 0 there. Okay, and finally I add second row to the first multiplied by 2 and third to the first multiplied by 2. R1 goes to R1 plus 2R2, and also R1 goes to R1 plus 2R3. and I get matrix identity. Yeah, identity matrix. Okay, so uh, we got identity matrix. This is a reduced row echelon form of my original matrix. And since it's identity, rank is preserved when we perform elementary row operations. So rank of A is a rank of identity is 4. Okay, this solve this problem, but let me give another solution. If at some point you don't like elementary row operations, you can proceed in a different way. Let me remind you that this matrix is minus 1, 2, 2, 0, 2, minus 4, minus 3, 1, 0, 1, 3, 2, 5, 1, 2, 0. Okay, we already know from the solution to this problem that rank of this matrix is 4. So determinant is not 0. And vice versa, if you have square matrix, determinant is not 0, then it's reduced row echelon form as identity matrix. So since we can use this result, so basically it's enough to solve this problem, it's enough to show the determinant of A is not 0. But we compute it, yeah. For example, we can take this row and we start computing, expand. Okay, maybe not this row. Let me take this. I like this more. This column, and we can start computing expand determinant of this 4x4 matrix by this column. Let's see what's gonna happen. 0 give us 0, then we get, so it should be plus, minus, plus, minus, plus. We get 1 times determinant of this 3x3 matrix. Oh, this is gonna be harsh. Yeah. 2 minus 4. Oh, no, sorry. Minus 1, 2, 2, 0, 1, 3, 5, 1, 2, plus, okay, sorry, minus 2 times determinant of the matrix obtained from A by removing this row in this column, which is determinant minus 1, 2, 2, 2 minus 4, minus 3, 5, 1, 2. Okay, this is gonna take some time, but you know the formula for determinant 3 by 3. You can compute determinant, and you find that it is not 0. Okay, it's time consuming, but this is pretty straightforward. Yeah. Very similar actually how to do elementary row transformation. Also boring, but in different style. Okay, good. Anyway, this problem is solved. Let's go to next problem. Next problem is A6. Okay, so we have a matrix M minus 3, 2, 1, minus 4. And the part A is to find characteristic polynomial of this matrix and its eigenvalues. Yes, characteristic polynomial of a 2 by 2 matrix, it's lambda square minus trace. Trace is the sum of diagonal elements. 7 minus 7 times lambda plus determinant. Determinant is minus 12 minus 2 minus 14 actually. Right? No, sorry, 12 minus 2 plus 12. Yeah. Minus 3 times minus 4 minus 12. Yeah. Okay. Characteristic polynomials. So we have, we can simplify it like this. And of course, we can factorize it like this. Sorry, was a mistake. It was 10. 10, 12 minus 2, 10. Yeah. Okay. So lambda 1 is minus 2, the first eigenvalue, and lambda 2 is minus 5, second eigenvalue. Again, eigenvalues of a square matrix are real roots of its characteristic polynomial. Okay. This is done. Part 1 is done. Part B, it's a little bit unusual since we didn't cover this topic. So the question is, so matrix is still the same. And the question is, what's the area of this following subset M times xy such that x squared plus y squared less than or equal to 3. Okay, look, if you remove here M, so what this equation defines? This equation defines a circle of radius root of 3 by the formula pi r squared, formula for the radius of formula for the area of a disk. To be precise, it's not a circle, it's a disk. Yeah. We get that the area of this guy is 3 pi. But then one of the properties of the determinant of a linear transformation, you have linear transformation, and you compute its determinant. This show how areas of, it's a scaling factor for the areas. Yeah. Imagine if you have linear transformation, you multiply x coordinate by 2 and y is the same, which correspond to the matrix 1, 0, 0, 2. Yeah. So we know that area doubles. Yeah, determinant is 2. So the area of this subset is the area of image of the circle when we apply M. And this is the area of original circle multiplied by determinant of M. Determinant of M is 10. So we get determinant of A times 3 pi, which is 30 pi. Okay, we didn't cover this topic. It's a geometrical meaning of determinant. So it will not be examined, but this is just a part of this 2016 exam. Okay, let's go to the next question. Okay, calculus, and okay, finally linear algebra. It's a question B3. Okay, we have 3 by 3 matrix A. Some, we don't know it, but we have 3 by 3 matrix A, such that the kernel of A is a span of the vector 2, 3, 4. And we know that A times minus 1, 2, minus 5 is 3, 0, 1. So the question, find all solutions of the matrix equation 3, 0, 1. Find all vectors x bar in R3 such that this is true. Yeah. But again, to solve such system of equations, we have to find the kernel of A, which is done. And this is kernel of A, it's basically homogeneous equation which correspond to this non-homogeneous equation. And then we have to find one particular solution. We already found one particular solution. And then all solutions is just the sum of kernel and this guy. So the answer is -1, 2, 5 plus t times 2, 3, 4, where t an integral number. So this part is just a kernel. This is one particular solution of this equation. And the solution, all solutions of this equation is just a sum of your particular solution and all solutions to homogeneous equation. So this is our answer. Okay. This was actually, so this was part A. Part B is to find 3 by 3 matrix whose kernel is a span of vector 2, 3, 4. There's infinitely many matrices like this. For example, you need to take a basically matrix whose rows are orthogonal complement, form a basis of orthogonal complements to this guy, to this vector. How about this? We can take -3, 2, 0. This vector is clearly orthogonal to this. If you take dot product, you get 0. And then you have 0. For example, -4, 3. Yeah. You can check that if you multiply this matrix by this vector, you get 0. Because when you multiply this matrix by this vector, basically what you do, you take a dot product of rows of this matrix and this vector, and we choose them in a way that the dot products are 0. So, yeah, so this vector definitely contained in the kernel. On the other hand, these first two rows are linear independent. So the rank of this matrix is at least 2, but last row is 0, so it is at least at most 2, so it's 2. Yeah, so its nullity by the rank nullity theorem is 1. So it means if you know one non-zero vector in the kernel, it should span the kernel. Yeah, this is non-zero, it's in the kernel, it spans the kernel as required. So this is this matrix is give us the answer. An answer. There's infinitely many answers. Okay. Part C. Suppose you have C is a 2 by 5 matrix. What's possibility for its rank and nullity? Okay, rank could be it's 2 by 5, 0, 1, 2. So nullity by the rank nullity theorem, 5 minus 0, 5 minus 1, 5 minus 2. And now we have to provide examples. Yeah, I take the simplest examples. This is matrix of rank 0, nullity 5. This is matrix of rank 1, nullity 4. And this is matrix of rank 2, nullity 3. Yeah. So this matrix is known. It's determinant 1, it's identity, so it implies that rank is at least 2, but of course it's at most 2, because rank cannot be larger than the number of rows and number of columns. Remember, rank is the maximal number of linear independent rows and at the same time maximal number of linear independent columns. Okay, this is everything with problem B3. Let's go to the next problem. Okay, I like this one. This is problem B4. So part A. So we have two linear operators from Rn to Rn, S, and from Rn to Rm. And part A asks us to prove the following. So if lambda is a real number, non-zero, that is an eigenvalue of S composed with T, eigenvalue of S composed with T, then lambda is an eigenvalue of T composed with S. Okay, by definition, okay, we have to prove this. We have to prove this. By definition, what does it mean? Lambda is an eigenvalue of T. It means that there exists a vector such that you apply, there exists non-zero vector V. You apply this operator to V and you get lambda V. Okay, now observe that we left on the right hand side where it lives. So V lives in Rn. Yeah. So left on the right hand side lives in Rn. Here we first map this vector V to Rm, and then we apply S and map it to back to Rn. So we can apply T again to this. Yeah, we can take T of S compose T V. This is T of lambda V, but T is a linear operator. So this is lambda T of V. Yeah. And this is just T of S of T of V. But this is by definition T composed with S applied to T of V. So if T of V is non-zero, it is by definition an eigenvalue, an eigenvector with eigenvalue lambda. So again, if T of V is a non-zero vector, then by definition lambda is eigenvalue of T composed with S. Yeah, because these two guys are the same. So the only thing we have to prove that T of V is not zero. But if T of V is zero, observe that this is S of T of V. So if S of T of V is zero, then S of zero is zero. Then we have lambda times V is zero, but lambda is not zero. So it means V should be zero, but V is not zero by definition of lambda being eigenvalue and V being eigenvector. So we prove that T of V is not zero. So this equality implies that T of V is an eigenvector with eigenvalue lambda. Good. Okay, this was problem A. It's solved. Problem B asks us to prove that this is no longer true if lambda is zero. So basically give an example to show that zero may be an eigenvalue of S of T, but not T of S. Okay. So we need example such that zero is eigenvalue of S of T, but not an eigenvalue of T of S. Okay, so here to produce examples, it's psychologically easier to work with vectors and matrices. So let's just translate this into matrices. In matrix language, we had operator from Rn to Rn, yeah, and we had, this was S, and we had T, linear operator from Rn to Rn, yeah. Okay, so S correspond to a matrix M times N matrix S. It's a standard matrix of this linear transformation S, and T correspond to N times M matrix. So we need to cook up such matrices. How about this? So let me call this A, and let me call this D. So I want example such that A, B, this is correspond to, so other way around. When we compose composition of S and T, if we take standard matrix, then this is just a product. Yeah, we first apply T and then we apply S. So this is A times B. And standard matrix for T composed with S, this is just BA. So we want example such that of a vector. We want to find example of A and B and vector V such that A, B, V is 0. So this means that 0 is an eigenvalue, but BA, eigenvalue of BA are not 0. Say U is not 0 for every U, not 0. Okay. How about this? How about put it this way? From the part C of this problem, we already know that this is impossible when M equals to N, and we will prove it in a second. So we need M to be different than N. So how about this? M is okay. M is 1, N is 2. Yeah. So we need to find 1 times 2 matrix. How about A to be 1, 0? And how about B to be, this should be 2 times 1 matrix. This is right. How about this 1, 0? Again, we're cooking up example. What is A times B? A times B, okay. It's going to be just number 1. Of course, number 1 doesn't have eigenvalue 0, so let me just swap them. Let me put this to be B, and this is to be A. Yeah. Then AB, matrix AB. What is this? This is a matrix 1, 0, 0, 0. Yeah, indeed, we can find vector V. In this case, this is AB, and V is just vector 0, 1. So 0 is indeed eigenvalue of this matrix AB. But BA, in this case, it's number 1. Yeah, this is just 1 times U. And U, in this case, so V lives in R2, and U have to live in R1. So R1 just a real line, so U is just a number, non-zero number. So BA is a linear transformation, basically multiplication by 1, so just 1. Yeah. Okay, so we are done. This is give us example in the language of matrices. Let's translate back into the language of linear operator. Again, M was 1, N was 2. We have N was M was M N was 2, M was 1. So S was linear operator from R1 to R2, and T was linear operator from R2 to R1. And let me recall that S was 1, 0, 0. And the standard matrix of T was 1, 0. Yeah. So basically this means that S of x is just a number. It's x0, yeah, and T of xy. I just write in the formula for S and T. This is just x. Yeah. Good. So what is S composed with T? You take vector xy, you first map it to the number x, and then you map it to the x0. Yeah. Okay. Good. So of course, if you take vector 0, 1, it's going to map to 0. So 0 is the eigenvalue. And T composed with S, take number x, map it to x0, and then map it back to x. Yeah. Okay. So this is an identity operator. Oh, this is identity. Yeah. Identity transformation. And this is just a projection to the x-axis. Okay. Let's give us a counterexample for part B. Yeah. Now let's do part C. We assume that M is n, and we have to prove that if 0 is eigenvalue of S composed with T, if and only if 0 is eigenvalue of T composed with S. Okay, we just, as we already did, we can translate this into the language of matrices. It means that 0 is eigenvalue of S times T of these two matrices, standard matrix of S, standard matrix of T, and this means 0 is eigenvalue of T times S. But now we can go further. We can translate this into the language of determinant. So we have to prove that this is true. This is equivalent to proving this is true. But these two statements are equivalent that determinant of S times T is not 0. So this line is equivalent to this equality. Because we know that for square matrices, basically almost by definition, 0 is eigenvalue if determinant is 0. It follows from the fact that eigenvalues are roots of characteristic polynomial. Yeah. And this similarly equivalent to the equality determinant of T times S is 0. Yeah. This is equivalent to this, and this yellow thing equivalent to this. Okay, but these two guys clearly equivalent. Why? Because determinant of product of two matrices, it's a product of determinant. So determinant of this product, determinant of this matrix times determinant of this, but this is the same as this guy. So this proves that 0 is an eigenvalue of S composed with T, if and only if 0 is eigenvalue of T composed with S. Okay, good. This solved problem before. Let me check. Okay, this was the last problem. Okay, we are done. So I stop the recording. You see, this is not so bad.